Okay, and we are recording. All right. Last time we talked about section 9.3. Well, we started section 9.3 dealing with the expected value. And the way we find the expected value, we just take the sum of the product of the outcome times its associated probability. Okay. We did a few examples of those. Let's see. The last thing I talked about also standard deviation, which is actually a measured spread. And in that case, you had to, there was a formula that I gave you at the end of class for doing the standard deviation. You had to first take the average of the data values, find the mean. Then for each individual data value, you had to subtract the data value minus the mean to get what they call the deviation from the mean. And then the square, and then you had to square each deviation. Okay, and then take the sum of those deviations, the sum of the squares of the deviations, and then compute the standard deviation by taking the sum of the deviation divided by the number of data values you have, and then take the square root. And that would give you the standard deviation of that entire data set. All right. Here where I left off, I need to talk about this. And we call this a measure of position using a z-score. Okay. And this is the blue box that talks about the measure of position using a z-score. Okay, you're going to let x be a number from a collection of numbers. The z-score for x is this number, and it's a z value, where z is going to be equal to the individual data value minus the mean divided by the standard deviation. Okay. Now, what a z-score or a standardized score tells us, it represents the number of standard deviations that particular x value is from the mean. And of course, the x is just going to be a raw score. The standardized score would be z. Question?
Would this be a method of determining whether the number itself is an outlier effectively?
That's going to be something else here, because that deals with the interquartile range. Yeah. Okay. Now, if z is negative, that means that your x value is going to be to the left of the mean. Or if z is positive, that means your x value is going to be to the right of the mean. Okay. Now, in this example, and I know this is probably hard to see, okay. So it said the average monthly rainfall in London is 6.3 centimeters per month, with a standard deviation of 1.14 centimeters per month. And the average monthly rainfall in Seattle is 8.08 centimeters per month, with a standard deviation of 4.57 centimeters per month. Now, suppose during a particular month, it rained 7.67 centimeters in London and 12.88 centimeters in Seattle. Which city received relatively more rain than usual? Okay, so here we're going to be comparing the rainfall amounts of 7.67 and 12.88 centimeters for the two cities that have different means and standard deviations. Starting with the one in London. For a rainfall of 7.67 centimeters, we use this formula. That's 7.67, that's the x value, minus the mean of 6.3. That difference will be divided by 1.14. Okay, so 7.67 minus 6.3 is 1.37. That's what this is equal to. So that 1.67 divided by 1.14 would be approximately 1.20. And this is rounded to 2 decimal places here. So the Z-score for rainfall of 7.67 in London is approximately 1.20. Now for Seattle, this might be hard to see, the rainfall there was 12.88 centimeters. So we take 12.88, subtract from it, the mean for Seattle was 8.08. And that would give us like 4.80, I believe. And then divide that by the standard deviation of 4.57. That would give you approximately 1.05. Okay. So we just compare those Z values to find out which one has received relatively more rainfall. Okay. So the rainfall in London is 1.20 standard deviations above the mean, while the rainfall in Seattle is 1.05 standard deviations from the mean. So in this case here, London received relatively more rain than Seattle compared to the city's usual amount. Okay. That's how we use Z-scores to compare two different situations here. Questions on this? Okay, look at problem number 11. This came out of the textbook on page 543. Joey took a quiz in his math class. The mean was 72 points, and the standard deviation was 10 points. Mitchell scored 86 points on a quiz in his history class, which had a mean of 74 points and a standard deviation of 5 points. What is the minimum score that Joey should have earned to score relatively higher than Mitchell? Okay. So I'm going to break down some things that we already know. All right, for Joey, we're trying to find out the score that he needs in his math class. Okay. So he took a math test where the mean was 72 and the standard deviation was 10. And I'm using S for standard deviation. And Mitchell got a score of 86 on his history test or history quiz. The mean there was 74 and the standard deviation was 5. Okay. I'm going to stop sharing my screen so that everyone can see this. Okay. Now, I do know Mitchell's score of 86 and the mean was 74 and the standard deviation was 5. So I can find out what that Z-score is. That's, of course, the X1 is the mean divided by the standard deviation. So here, Mitchell's quiz score was 86 minus the mean on that history quiz was 74 divided by the standard deviation on that quiz in history. That's 5. So if I do 86 minus 74, I'm going to get, let's see, 12 And 12 divided by 5, 2.4. So using Mitchell's score of 86 on the history quiz, the z-score there would be 2.4. And then that question that asks, what is the minimum score that Joey should have earned to score relatively higher than Mitchell? Well, the z-score there was 2.4. So we're going to use that to find out what would be the minimum score he would need. So I'm still going to use that z formula. Z is equal to the x value minus the mean divided by the standard deviation. So here your z is 2.4, because that's a z value on Mitchell's history quiz. So we're going to use that. And that's going to be equal to the x value is what we're looking for. That's Joey's quiz score on that math quiz, minus the mean on the math quiz was 72, divided by the standard deviation on that math quiz was 10. Okay. All right, so now we can kind of try to solve this equation for x. And what I would do here, I would put 2.4 over 1, and then do what they call cross multiplication. So if I do 2.4 times 10, or 2.4 times 10, that's 24. And that's equal to 1 times the x minus 72. Well, if I distribute the 1 of the x, 1 times x, that's x minus 1 times 72 is 72. So I have an equation of x minus 72 equals 24. And then to solve for x, I'm subtracting 72, so I need to add 72 on both sides. So that means x is equal to 96. So for Joey to relatively score higher than Michael, he would need, than Mitchell, then he will need a 90, well, at least a 96. At least.
So 96 and not one higher. 96 would be equal to, wouldn't be more than.
He could, but well, you can just say more than 96. Just say more than 96. All right, any other questions about problem number 11? Okay. All right, problem number 12. Ben scored 82 on a history test, which had a mean of 74. Molly scored 88 on a math test, which had a mean of 80. The z-score for Ben was 1.4, and the z-score for Molly was 0.8. Which class had test scores with more variation? So in other words, we're trying to find the standard deviation for each one of those and find out which one had more variation, which is a spread, more of a spread of the data. Okay. So again, I scored an 82 on its history test. The mean there was 74. and Molly scored 88 on the math test, and that had a mean of 80. And the Z-score for Ben the Z-score for Ben, that should, I'm gonna say Z is equal to 1.4, and the Z-score for Molly was 0.8. So now we need to find out what the standard deviation is for each one of these. So I'm gonna start with Ben's score. Using this formula, Z is equal to X minus the mean divided by the standard deviation. And his Z-score was 1.4, equals to his test score or quiz grade of 82 minus the mean of 74 divided by the standard deviation. I'm gonna let S be the standard deviation, since most textbooks use S as the standard deviation. Okay, so now what I need to do here is this. I need to get rid of the S that's in the denominator. And we do that by multiplying both sides by S. So on this side, I got 1.4 times S is equal to, let's do 82 minus 74. It's 8. Okay. And then to solve for S, I'm multiplying by 1.4, so I need to divide both sides by 1.4. So that,
5.7.
okay.
5.7.
Okay. So the one decimal place will say 5.7. Okay. And now for Molly, we're going to find out what that standard deviation is. Using that same Z formula. Let's see, her Z-score was 0.8. It's equal to X, that's the test score, 88, minus a mean of 80, divided by, and I'm gonna let S again be the standard deviation. All right, so to get rid of the S that's in that denominator, we're gonna multiply both sides by S. So in this case here, this will be 0.8 times S. That's equal to, these S's are gone. What's 88 minus 80? It'd be 8. And then divide both sides by 0.8. S is equal to 10. Okay. All right. So now we need to find out which class had test scores with more variation. Okay. So these are for history. I should say here, this is for history down here. And the one for the standard deviation of 10, that's for the math scores. So the one with the highest standard deviation is the one that has more variation. And it would be those math scores. Okay. So the scores on the math test had more variation. That means the data there was spread out more for those math tests than they were for the history tests. Okay. Any questions about problem number 12? All right, next we'll look at normal probability distributions. Okay. Now, we mentioned three important aspects of a quantitative variable: the measure of center, the measure of variation, and distribution. And if you recall, measure of center deals with things like the mean, the median, and the mode. And the measure of variation deals with things like range, talk about mean absolute deviation, and also standard deviation is a measure of variation as well, because that deals with the spread of the data. Now we're going to look at distribution. Now, distribution tells us about the shape and pattern of possible values. And we can use a graph to display the shape and pattern of values. And what the distribution does, it gives us a sense of the possible values of a variable and how often these values occur. Okay. So for a discrete variable, such as the outcomes, when we roll the die or spinner, we could use a table to display that distribution.
What's the definition of discrete they're using there?
Okay, the word discrete is just a finite number, like these numbers right here. 1, 4, 5, 6, and 7. Those are discrete, because that's something that we can count.
It's not.
Yeah. Mhm. Okay. Any other questions?
What's its opposite?
We also have continuous variable. Usually it's going to be something that, a variable where a value can be measurable. It's usually going to be in the form of a decimal. Any other questions? Okay. In this case, let's consider the spinner with 8 equal size sectors that have these numbers: 1, 4, 4, 5, 6, 7, and 14. Then the mean will be 6. And they just added these numbers up and divided by 8. And then they used the standard deviation formula to come up with 3.5, rounded to 1 decimal place. And we can display that distribution using probabilities. And let me move this out the way so y'all can see this. Okay. Back here it is. And there's only one way of getting for them obtaining a 1. So 1 divided by 8, that's 0.125. 2 ways of a 4, that's 2 divided by 8 or 0.25, and so on. That's where these decimal values are coming from. Next is, what was that?
I think I'm from 3.5 to 0.125.
Wait a minute, that 3. Okay, let's go back. That 3.5, that's just a standard deviation.
Right.
These are just the probabilities for getting each one of these individual numbers here. Like for the 1, they only got one out of 8 equal size sectors. So that's 1 divided by 8, which is 0.125.
Sorry.
Okay. All right, any other questions? Okay. For many variables, such as the height or blood pressure, we can use a histogram to display a big picture of the shape and the relative frequency with which values occur in different intervals. So here, is a histogram that is symmetric with the shape of a bell, as you can see. And this is something that we call a normal distribution. Another way for that is, another word or another phrase for it is, if we were to graph it, it would be the bell-shaped curve. Okay. So if quantitative or numerical data have a symmetric bell-shaped histogram, then the variable is said to have a normal distribution, which is a bell-shaped curve. And as you saw in that last slide, the peak of the bell is above the mean. If the histogram displays the relative frequencies or percents, then the total area of those rectangles is 1. So in other words, this area below this curve has to be equal to 1. That's always the case for any normal curve.
Has to account for all the data.
Yes. Mhm. All right. Any other questions? Okay. So if you have SAT scores and you're told that they're normally distributed, what do we mean by that? Well, here it is. Let's say we take a random sample of many SAT scores, create a histogram for that data. Then that means you should expect to get a histogram that's going to be symmetric with the shape of a bell. Okay, so those data values there will form a histogram, and the histogram should be in the form of a bell-shaped curve. So those test scores would be normally distributed. Okay. All right, next we're going to talk about this particular rule, the 68-95-99.7 rule. Another name for that would be the empirical rule, spelled E-M-P-I-R-I-C-A-L. All right, up here.
Oh, okay.
Empirical rule. And for those of you who are watching this through Zoom, that's the word I was talking about, empirical.
So that's what they're referencing when they say the words like shifting developer.
Yeah. Mhm. Okay. An amazing aspect of a variable such as the heights or test scores that is normally distributed is that we can say something about the percent and therefore probability of observations that should belong to intervals. So here, the only thing we need to know is that the shape of a histogram meets our description, along with the mean and the standard deviation of the data. All right, so here is that rule for normal distributions. And we're going to assume or suppose that data has a histogram that is symmetric and shaped like a bell. Okay, here's rule number 1. Approximately 68% of the data values fall within 1 standard deviation of the mean. So here we got X bar, which is the mean minus the standard deviation, and X bar plus the standard deviation. That interval represents 1 standard deviation of the mean, 1 below and 1 above. And then the next bullet point is where 95% of all the data values fall within 2 standard deviations of the mean. So here they got X bar minus 2S and X bar plus 2S. 2 standard deviations below the mean, 2 standard deviations above the mean. And then finally, 99.7% of all the data values fall within 3 standard deviations of the mean. That's 3 below and 3 above the mean. And this, I might be able to show this to you in the form of a bell-shaped curve so that we'll see visually what that means. So here's the normal curve right here. All right, the mean, which I'm gonna call X bar, that's in the center of that curve. So here, if I go 1 below and 1 above, and each one of these represent a standard deviation. So 1 below would be that mean minus 1 standard deviation, and 1 above would be the mean plus 1 standard deviation. Okay, so this represents 68% within 1 standard deviation of the mean. And then if I go another standard deviation below and above, this will be X minus 2 standard deviations. And this one will be X bar plus 3 standard deviations. So from here, all the way out to here, that's 68. From here to here, that's 95% of the data values within 2 standard deviations of the mean. And this should be 2S, not 3S. So if I go 1 more standard deviation below and 1 more standard deviation above, this is X bar minus 3S, and this one would be X bar plus 3S. So from here to here, that's this area here. This represents 99.7% of those data values that are within 3 standard deviations of the mean. Okay. So this is just a visual way of using the normal curve to show you how many standard deviations, what the percentage of data values that will lie within 1 standard deviation, 2 standard deviations, and 3 standard deviations of the mean. For this, we go no further than 3, above and below. Okay. For this particular rule. All right, any other questions? Okay, here's the concept map of that, of what I just showed you. Here I use the normal curve. So here, 68, then 95, and then 99.7. Okay, let's say we had something like this. The mean SAT score for high school students on the mathematics portion of the test in 2010 was 516, with a standard deviation of 116. Assume the scores are normally distributed. Estimate the percent of students with the following scores. And these are it between 400 and 632, part B between 400 and 748, part C less than 400, and part D more than 284. Okay, so here is how they do this. A number line is drawn with a mean of 516 in the center, and then number the equally spaced tick marks that are 1, 2, and 3 standard deviations from the mean. And here it is, as you can see. So here the center, that's the mean, 516. So here, if we go to the left, that standard deviation was, what was it? It was 116, okay. So if I go one below, I have to subtract 116 to get 400. If I go one below that, I subtract another 116, that would give me 284. And then to go one below that, we subtract another 116 to get 168. Okay, and then to get these numbers on the right side, we had to add 116. So 516 plus 116 would be 632. And then 632 plus another 116 will be 748. And then finally, 748 plus another 116 will be 864. Okay, so this represents our empirical rule with the 1, 2, and 3 standard deviations from the mean and those values assigned to it. Okay, so now we're going to use this to answer those 4 parts in that original problem. Okay, so for example, 68% of the students of the scores are between 400 and 632. That's 1 standard deviation of the mean, which means 34% of the scores belong in each half of the interval. And that 34% is this. You take half of 68 to get 34. In addition, 95% of the scores are between 284 and 748. And if we do 95 minus 68, that would be 27. And then 27 divided by 2 would be 13 and a half. And then 13.5% of the scores fall between 284 and 400, as well as between 632 and 748. So this is what we have here. And it's going to mean 5% of the scores were below 284 and 780. This should be 748. Okay. And because of symmetry, that means 2.5% of the scores are below 284 and 2.5% are above 748. So here. And here they've broken it up like this. Right. Any normal bell curve. So let's answer some questions here. Like in part A. Between 400 and 632. Well, here's 400 and here's 632. If this is 34 and that's 34, that distance there, we add 34 and 34 to get 68%. So that means that 68% of the SAT scores are between 400 and 632. And in part B, between 400 and 748. Well, here's 400. This is 748. So here we're going to add 34, 34, and 13.5 to get 81.5%. The 34, this 34, and 13.5.
So it starts at 400?
Yeah.
What's the difference between going up to the 632 and starting at the 284, counting that 13 and then those 34s?
Well,
I mean, either way, we still be 81.5, right?
well, see, here's 400 right here. So that can go from 400 to what, 748. That's this space That's this area right here in between. So it's gotta be this, this, and this.
But not the one on the other side.
Not on the other side.
Okay.
All right, any other questions?
I think I just how you get the percentages. Maybe I missed.
Okay,
15.
okay, let me do this. I can show you up here. Because I know that's gonna be hard to understand. Let's say the mean is right here at the center. All right. That represents 68% of the data values that are within one standard deviation of the mean, which means if these are spaced out evenly, and if I take half of 68, that's 34, on this left side of the mean, and on this side, also 34%. Okay. And now, let's go out 2 standard deviations of the mean. Now, according to the empirical rule, or the 68, 95, 99.7 rule, 95% of the data values are within 2 standard deviations of the mean. We've already got 34 and 34, that's 68. So if I subtract 68 from 95, that's going to be 27%. And these areas are spaced out evenly. So divide by 2. So this is 13.5% here and 13.5% here. And then finally, 3 standard deviations to the left and to the right. And it says 99.7% are within 3 standard deviations of the mean. So, and all of this represents 95%. That leaves us with 4.7%. Divide that by 2, that'd be 2.35%. So this is 2.35%. And the other one is 2.35%. Okay. Now the whole curve is 100%. And we already got 99.7% taken care of. That's going to be 0.3%. Split it in half, you're going to get 0.15%. So to the left of this is 0.15%. To the right of that is 0.15%. Okay. So that's where those percentages are coming from. Any other questions? Okay, so now let's go back to.
No, no, sorry.
I just want to go ahead and clear everything up before we move on here. Okay, so now. Oh, it's on. Yeah. So I guess we got part A and B taken care of. So now part C, where it says less than 400. Here's 400 right here. Everything to the left of that is less than 400. So we got to add 13.5%, 2.35%, and 0.15%. If you add those together, you will get 16%. That represents the percentage of students whose SAT score is less than 400. Okay. And finally, part D, where more than 284. Well, take a look, here's 284 right here. More than is everything to the right of 284. So you got to add 13.5%, 34%, another 34%, another 13.5%, 2.35%, and 0.15% to end up with 97.5%. So 97.5% of the test scores were more than 284. Okay. Questions on that? Okay. Let's look at problem number 51. Says that the mean SAT score for high school students on the writing portion of the test in 2010 was 492 with a standard deviation of 111. What percentage of students have the following scores? And in part A, we got more than 714, part B less than 381, part C between 381 and 714, and part D between 270 and 492. Okay, so let's look at this particular problem here on the board. And we're told that the test scores, the mean SAT score was 492. That's the number that's going to be in the center. And we're told that the standard deviation was 111. So let's find out what our values are. That's going to represent 1, 2, and 3 standard deviations on each side, starting with the left. If this is 492, then one standard deviation to the left of that, I have to subtract 111 from 492. And I come up with 381. And to the left of that, I'll subtract another 111, and that would be how much? 270. And then another standard deviation to the left of that, I'll subtract 111 from 270, that will be 159. Okay. Now let's look at the numbers to the right. And that's one standard deviation above. 492 plus 111. 603. And then the next data value that represents 2 standard deviations above the mean, add 111 to 603, you'll get 714. And then the next test score that represents 3 standard deviations to the right would be 825. Okay. So we're going to use this to answer these questions. What percentage of students have scores more than 714? So here's 714. More than is everything to the right of that. So we need to look at these percentages that are to the right of 714. 2.35% plus 0.15%. That's how much? Anyone? 2.5%. So 2.5% of the test scores of the students had test scores that was more than 714. And part B, less than 381. Well, here's 381. We need to look at the numbers to the left of 381. That's these percentages right here. 13.5%, 2.35%, and 0.15%. What would that equal to? 16%. Meaning 16% of the students had an SAT score less than 381. Okay, and then part C, between 381 and 714. Let's see, here's 381 and there's 714 right here. So we have to look at the percentages that are between 381 and 714. That would be 34 plus 34 plus 13.5%, which would be how much? 81.5%. And finally, part D, between 270 and 492. So here's 270, here's 492. So we're looking at 13.5 and 34%, which would give us how much? 47.5%. Okay, so 47.5% of the students had SAT scores between 270 and 492. Okay. All right, any questions about the normal distribution? Okay. All right, next we'll talk about usual values here. All right, usual values, of course, are defined as the one that seems reasonable or expected. Okay. And this is the rule of thumb for using the standard deviation to identify usual and unusual values. If you recall, we were dealing with usual and unusual values when we had something to do with the mean absolute deviation. This time, we're using the standard deviation to identify usual and unusual values. So let's let X bar and X represent the mean and standard deviation of a collection of numbers that can be displayed with a histogram that is symmetric and shaped like a bell. In other words, it's like a normal distribution. Okay. A usual value occurs when your z-score, or the X has a z-score from -2 to 2. So any z-score for an X value that's between -2 and 2, we consider it to be usual. Now the unusual values occur when your z-score is either less than -2 or more than -2. Now, in the new statistics book that I plan to use next in the fall, they're going to use the phrase significantly high and the other one's significantly low. So something that's significantly high would be where the z-score is more than 2. Significantly low would be something where z-score is less than -2. You don't have to worry about that in this class. But anything between -2 and 2 would be, any z-score between -2 and 2 would be usual. Now,
Same idea as ours.
it's the same idea. Mhm. It's just using different words. Okay, now the minimum usual value is going to be this, x bar minus 2 times s. That's going to be the mean minus 2 times the standard deviation. And that has a z-score equal to -2. And then the maximum usual value, that's going to be the mean plus 2 times the standard deviation. And that will have a z-score equal to 2. Okay, so you first have to find out what your minimum and your maximum usual values will be before you can determine whether or not whether the x value or with that z-score is going to be usual or unusual. Okay. So like in this example, the heights of 19-year-old males are approximately normally distributed, with a mean of 69.9 inches and a standard deviation of 3.5 inches, based on information from the National Health Statistics Report. Is a given height of a 19-year-old male usual or unusual, or an unusual measurement? So in part A, we got 73 inches, and part B, 79 inches. Okay. So on the next slide, this is how they show you how to do this. Here we have to use that Z formula, x minus x bar. X bar is the mean divided by S. That's the standard deviation. So here, for it to be usual, the z-score has to be between -2 and 2. So let's say here the z-score for 73 in this case. Here we have to do 73 minus 69.9 because that was the the mean divided by the standard deviation that was given to be 3.5 inches. So if we do 73 minus 69.9, that would be, I think, 3.1 divided by 3.5, that would be approximately 0.89. So for that height of 73 inches, that Z value is 0.89. And it is a usual height because 0.89 falls between -2 and 2. And part B, we use the same Z formula at the top. 79 minus 69.9, that would be 9.1 divided by 3.5, which is your standard deviation, that would be 2.6. Now that 2.6 is outside of the -2 to 2. 2.6 is bigger than 2. So that means 79 inches is going to be an unusual height. And if we want to be more specific, it would be a height that is significantly high. Questions on that? Okay, let's look at these two right here. This is a continuation part of problem 48, C and D. Now the data set consists of scores 42, 58, 60, and 52. Is 36 a usual or unusual value? And part D is 45 a usual or unusual value. Now we did parts A and B at the end of Monday's class. And we found out what the mean and the standard deviation was. Okay, now I'm gonna go ahead and give those to you instead of working them out. The mean was 53 and the standard deviation, we found that out to be 7 on Monday's class. So now we want to know, is 36 a usual or unusual value? Okay, so to find that out, we do C is equal to X minus X bar divided by S, and substitute in this particular formula. So here the X is that data value itself, 36, minus X bar, the mean, 53, minus S, the standard deviation, which is 7. And then we simplify this. 36 minus 53, that's going to be, and yeah, you're going to get a negative number, negative 17. And if we take negative 17 and divide that by 7, we're going to end up with negative 2.43. Now, based on the range of usual values from negative 2 to 2, is negative 2.43 usual or unusual? It's going to be unusual because negative 2.43 is further to the left of negative than negative 2 is. So that data value of 36 is unusual. Okay. Questions on part C?
Is it valid also to just do the min and max and see if it falls within? or outside?
You can, but once you do this, we know negative 2 to 2, that's the range of usual Z values. Any other questions? Okay, is 45 usual or unusual? So here's 45, and we're going to use that C formula. So here your X is going to be 45 minus the mean, 53, divided by the standard deviation of 7. So in this case, 45 minus 53 will be negative 8 divided by 7, negative 1.14. Now, does negative 1.14 fall between negative 2 and 2?
Yes.
Yes, it does. So here, that's a usual range there. So in this case, 45 is considered to be a usual value. All right, any questions about finding usual or unusual? Well, just usual values here. Okay, we'll stop right here. Okay, and I do have section, still have the rest of section of 9.3 to complete.
Do we bring 10 next time just in case?
Huh,
Will you post 10 just in case for next time?
yes. And once I finish that, there is a section 11.4 that I will cover.
Whatever the next one is.
Yeah, that's the next one. Hate to say it, but we're jumping from chapter 9 to a section in chapter 11 and then chapter 12. And I'll probably cover 2 sections of that before the semester is out. Okay. And for those of you who are Zooming, make sure that you type in your name in the chat box so that way I can count you present. And I will see you Monday. All right, have a good weekend.
Got it. So, yeah, so just make sure that when you're looking at these percentages, just pay it to the ball, that's. So here's your 274.